Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. We are from Group 6 from Separation Processes course of Section 2. So in this video, we are going to introduce you about liquid extraction, LLE. So what is LLE? This technique is usually used to separate and purify substances based on their solubility in two different liquids like oil and water. Then there are four main points that we are going to cover in this video, which are: the first one is the fundamental of LLE, followed by simple demonstration of LLE, then application of LLE in real life, and last but not least is the advantages and limitations of LLE.
Now let's have a look on this animation. First, we introduce the aqueous phase of liquid, and then we will insert the solute, and we include the organic liquids. So, as the solute is introduced into the system, the solute will preferentially partition itself between the two phases according to its polarity and the nature of the solvents involved. In a typical setup, one of the phase is aqueous and the other phase is organic. It is often a non-polar solvent like benzene, ether, or chloroform. So the solutes will start to behave in each phase, depends on its polarity relative to the solvent. Highly polar solids, for example, will interact more strongly with the aqueous phase, where hydrogen bonding and dipole-dipole interactions are prominent. As a result, solids tend to concentrate in the aqueous phase more, and they will leave the organic phase relatively free of the solute. Conversely, non-polar or low-polarity solids will exhibit a greater affinity for the organic phase, where non-polar interactions such as van der Waals forces dominate.
So, what are the key principles of the liquid extraction? The first one is partitioning behavior. The solids will distribute themselves between two immiscible liquids according to their solubility. It is often described by the coefficient partition, which is K is equals to C organic over C aqueous. C organic and C aqueous is the solid concentration in both organic and aqueous phase. Next, we have phase immiscibility. So in LLE, the two liquids used must be immiscible to each other. For example, we can use water and oil. This is to form the distinct layer upon mixing. Third is density difference. The liquid separates into layers due to their density difference. The less dense liquid will form the upper layer, while the much more denser liquid will form the lower layer. And then the last one we have in terms of mass transfer, the solids migrates from one phase to the another phase. It is driven by the concentration gradient until it reaches the equilibrium state.
So first, choice of solvent. To make sure the liquid extraction process can be done effectively, we need to choose a proper solvent. So how to know that we can choose a proper solvent? We need to take these 3 points into consideration, which is first, the solubility difference between the two phases, second, the partition coefficient of the solute in chosen solvents, and third, the chemical compatibility of the chosen solvent with the fit solution and also target compound. So next, we want to talk about pH. How pH can affect the LLE process? This is because the pH of the aqueous phase can significantly impact the extraction of ionizable compounds. So when we want to choose a proper pH, we need to take these 3 points into consideration. First, ionization state. It is because pH affects whether compounds are ionized or neutral. Next is about selectivity. pH adjustment can enhance selective extraction of target compounds. And third, buffer system. Since buffers are known to stabilize pH, it can ensure consistent extraction conditions. Next, I will explain about mixing intensity. Adequate contact between phases ensure efficient mass transfer. Proper mixing can allow for proper phase separations. So, how mixing intensity can affect LLE process? First, because the enhanced contact to ensure maximum contact between phases for efficient mass transfer. And next is about mass transfer, which it can improve rate by reducing boundary layers and enhancing solute diffusion. And third, homogeneity. By mixing, it can achieve consistent extraction conditions throughout the solution. Next, I will explain. Last but not least, I want to explain about temperature. Higher temperature generally will increase solubility and extraction rates. But how? First, we need to take into consideration about the temperature effects on partition coefficient. Next, we will also need to look about the influence on mass transfer rates and equilibrium. And third, about the pressure impact on critical solvent properties. Taking all of these points into consideration, we can choose a proper temperature to make sure the LLE process can be done effectively.
For demonstration part, the apparatus used is separatory funnel. Then the chemical used are aqueous solution and organic solution. So firstly, make sure to close the valve and then attach to the retort stand. Then pour the aqueous solution first, which is more dense liquid, followed by organic solution, which is the less dense liquid.
Now close the funnel properly as shown in the video. Shake the funnel manually and remember to pointing away the funnel from the body. Open and close the funnel to remove all the gases. Attach the funnel to the retort stand and remove the stopper immediately. Let the solution in the funnel settle down until there are 2 layers. Next, transfer the lower layer into a beaker by slowly opening the stopcock, placing the end of the tube at the beaker to avoid splashing. At the end, carefully control the flow of lower layer to avoid the upper layer solution flow into the beaker.
There are various applications of liquid-liquid extraction ranging from simple to industrial scale. In our daily lives, common examples include separating oil from water and brewing coffee. Coffee brewing is considered a form of LLE because water extracts the flavors from the coffee grounds. On an intermediate scale, liquid-liquid extraction is applied in the pharmaceutical industry and environmental science. In the pharmaceutical industry, LLE is used to extract natural compounds from resources to develop drugs and medicines. In environmental science, LLE is employed in wastewater treatment to remove undesired compounds. For industrial scale, liquid-liquid extraction is utilized in various industries including petrochemical, biofuels production, and chemical manufacturing. In these industries, LLE is primarily employed to purify and extract valuable products.
Proceed to the advantages and limitation of LLE. Let's start with the advantages. It is simple and efficient, making it a go-to process in many industries. It requires minimal operator training, meaning anyone can use it with ease. It is considered safe for the environment. LLE does not require energy-intensive heating, unlike distillation, with reduced carbon emission. And lastly, it yields a high-purity product. However, LLE isn't without its challenges. Here are some limitations. It often needs a large volume of high-purity solvent, which can be costly. The process can be time-consuming, impacting productivity. Emulsion may also form, which can complicating the separation. And finally, it tends to yield a small amount of product, which might not be ideal for large-scale operation. Understanding both its strengths and weaknesses help us make better decisions when choosing LLE or other unit operator. That's all for the advantages and limitations of LLE.
In summary, liquid-liquid extraction, which is also known as LLE, is a separation technique that uses two unmixable liquids to isolate components of a mixture based on differences in solubility. This technique is extensively used in various industries including pharmaceuticals, biofuels production, chemical manufacturing, and more, showcasing its importance in processes handled by chemical engineers. That's all from us. Thank you for watching and we hope that you enjoyed this video.